Hi, welcome back. So, as you can see, one of your teaching assistants, the illustrious and incredibly fluffy Earl, has decided to join us for our discussion of the replication crisis. So, one of the things that's actually kind of interesting, despite the fact that Ioannidis was mostly focused on all research studies. Like, I should mention that this replication crisis is not psychology specific. Part of the reason that it's been highlighted with psychology is because I think compared to a lot of other fields, psychology is actually taking a lot of responsibility for the replicability crisis that's going on in our field, I think in a way that other fields may not necessarily be doing. I would say the biomedical field actually has quite a bit of a replication crisis in and of itself. But for psychology, really, this focus on replication, despite Ioannidis' paper being published in 2005, didn't really come into play until maybe about 2010, 2011, right around the time that I was done with graduate school. And so to kind of put this into perspective, there are a lot of things that have really changed about our field in the past 10 years that I have had to pick up really rapidly because in 2010, 2011, 2012, these were not things that were necessarily expected. You were not necessarily expected to pre-register data or your hypotheses or your analyses. I made my data available to anybody who asked for it, but there was one thing that really kind of reverberated throughout psychology like a shockwave. And I remember having lab meeting after lab meeting talking about this paper. So basically what happened is that around 2010 and 2011, Daryl Bem published a paper in the Journal of Social Psychology and Personality, or Personality and Social Psychology, so it was like JPSP, basically published like a series of like 11 or 12 experiments that basically suggested that ESP was real. And at that point, a lot of, and that was more of a social psychology journal. I know that in my lab and with a lot of the different professors in my area, there was basically outright dismissal. He got this published in a pretty prestigious journal. Several studies purportedly showing the existence of ESP. There must have been a problem with the stats or the way that the data was collected, and it's kind of clear we've got a replication crisis because if you can show the evidence of ESP, then and you've supposedly done it in a roundabout way, in a thorough way, what on earth is going on with our field that something like this can actually get published? And so at least for a lot of psychologists at the time, this was really the thing that changed things, was this publication of the ESP study by Daryl Bem. So let's talk about what this means. Now, when you put together what I mentioned before, selective publication where we're only publishing findings that are significant, we're not publishing replications, and we're pushing people to get to this statistical significance, a world where our p-value is 0.05 or smaller, and we don't support replication, and we do not support negative findings, you get questionable research practices, or QRPs. These little sketchy things that are technically unethical that people will do to make their data significant and to make their data say something that it doesn't. And this can include a variety of different things. So here are a couple of examples, and you'll hear me talk about these again and again next semester. So maybe if our first attempt doesn't work, we make the participant's task easier and start again. Now, there is definitely a place for this. It's called a pilot study. You do not necessarily run your data over and over again until you get the study that you want, and then you publish it. You can pilot and see if the task is too hard, but that's a pilot study, and you should probably report that you did a pilot study. But that's still a pretty questionable practice. Now, I've heard about this, and I've been grateful to never be in a lab that supported this, but I've heard from friends and colleagues about other labs that have done this, and it is sketchy. I have been told, figure out how many people you want to collect data for ahead of time, and do not look at your data until you've got all of those people. If you look at your data ahead of time, like before you've collected it all, and then you look at it again when you collect it, you're technically supposed to take a statistical penalty, but that's not what everybody does. So some people will run 20 participants in each group, look at the data, and then basically keep running and adding people until you get the results you want. You are not supposed to do that at all. Specify how many people you want ahead of time and only look at your data once you're done. You note a few outliers and exclude those aberrant results. There is nothing wrong with necessarily excluding outliers, but you need to have a plan for how to exclude outliers before you collect your data. You need to specify how much of the data that you've removed. So when I've removed outliers, they are usually maybe less than 1% of my total data. And you make very clear what your criteria for removal is ahead of time. You don't wait until you look at the data and you're like, you know, if we remove these outliers, this data would look perfect. I'm going to remove them. There's our perfect data. Don't do that. Don't ever do that. Additionally, we can get multiple measures of performance, but one's easier to measure and seems to give more consistent results, so we drop the other two and we never talk about them. I use multiple measures in my studies, and I report the results of every single one, whether they square with what I expected or not. That's what you're supposed to do. All of these are questionable research practices, and no psychology subfield is immune. Like I said in the last lecture, cognitive psychology might replicate more findings better, but they're number 2 in questionable research practices. We all have room to do better. So all of these processes, by the way, particularly this one, making sure that you have enough data and making sure that you just keep running participants until you get the results you want, this is what's known as p-hacking. What you're basically doing is adding people and adding people and adding people until you get that p being less than 0.05. And this is something that you do not want to do. Now, this has a lot of unfortunate effects for our field. Generally, as I've kind of mentioned, journals prefer innovative findings. They want to publish new things. They don't publish replications. And as a result, there's little incentive for people to try to replicate. In fact, one of the ways to solve the replication crisis that has been suggested is that in methodology classes, such as this one, we should be doing more replication to really highlight the importance of it, which is why, since as of last year, I've been doing a replication study as your project rather than coming up with something new. So there's little incentive for replication. And so few replications are done, let alone even finished. And worse, those that are finished, these studies may actually fail to replicate. So here are a couple of different examples of findings that have failed to replicate. So the reproducibility project from the Open Science collaboration from 2015, they were trying to replicate 100 studies. 36 replicated perfectly, 64 didn't. Many labs won 13 studies, 36 sites, 634 participants, standard protocols and materials. 10 of these findings replicated, 3 didn't. Many labs 3, 10 studies, 20 sites, 2,696 participants with standard protocols and materials, 3 replicated, 7 did not. And here's the thing. Because we don't publish negative findings, these studies that aren't replicating tend to be regarded as being established. They're significant. There's no need to go against them. They've already been published. Why would you want to try to knock that study down? But that study was a fluke. And because we don't really value replications in this field, this study's fake. We're taking it as gospel when we really shouldn't be. And unfortunately, anybody who tries to say that study's not correct, basically they can't do anything about it because replications don't get published. Negative findings don't get published. So beyond this, why do replications tend to fail? So generally, these are because replications may fail because of context. So I've already kind of talked about experimenter-specific effects. There are certain instances where if you know the experimenter, or if you work with the experimenter, or if you have access to materials or very explicit instructions that the experimenter has, you're going to get the effect. If you aren't in contact with the experimenter, you won't. So that's very contextually sensitive. You have a different sample, or you have a different setting, and this is especially more likely to occur, these kind of failed replications based on context sensitive effects. This will happen if it's a very, very small effect. I kind of learned very, very quickly in undergrad, because of my failed replication with my honors thesis, that if I'm looking to replicate something, I should not try to look for an effect that is statistically small. I should be looking for larger effects that are robust and will hold up. And again, I would kind of argue that if an effect is pretty small and it only works under certain circumstances, it's probably not big enough that you'd notice it in the real world anyway. The number of replication attempts matter. Part of the reason that the fail rate for OSC, the Open Science Consortium, has been a little bit different than many labs is because many labs typically will do multiple replications of the same study at multiple sites. OSC has only done one. So sometimes you might have to do multiple replication attempts. There could be some issues with the original study. Oftentimes the sample size is too small. They could be doing what's known as harking, hypothesizing after the results are known. So let's say that I'm doing an experimental study. I'm looking at like 7 different variables, and I don't know what I'm going to get. I'm just doing an exploratory analysis. I don't know what I'm looking for. I just want to try this because I see it's fun. And then it turns out that one of my variables shows something really cool that maybe the other 7 or 8 really didn't. And so now I'm going to craft a narrative that I was always interested in this one variable. I center my whole report and my write-up on that one variable, acting like I knew what was going to happen ahead of time and that this is what my hypothesis really was, even though I had no idea what I was doing. I just plugged in 7 variables and this is the one that just happened to work. And I probably won't even report the other variables that failed because they don't really fit with this little fake story that I'm trying to create. So don't hark. Form your hypotheses ahead of time before you actually start collecting your data. That's why getting good background research is important. Background studies and doing a literature review can help you formulate the hypotheses that you want to have before you start collecting your data and kind of seeing what shakes out. Form your hypotheses before you even collect your data. And then also p-hacking might explain why replications fail. So how do we avoid questionable research practices? We need to specify our expected results in advance. Plan your analyses, plan your comparisons, plan how you're going to analyze your data. Don't hark. Consider exploratory analyses cautiously. If you're just wanting to see what happens, you need to be very clear that's what you're doing. And because you haven't specified results or analyses or hypotheses ahead of time, if you do get something interesting from your exploratory analysis, you need to be very cautious with how you report it. You should be very tentative with it because you didn't know what was going to happen ahead of time. And then additionally, you need to consider why you made certain choices in your analysis. Did you make these decisions before or after you saw the data? Generally, we're trying to move away from a post hoc analysis. You need to plan your analyses out ahead of time before you even look at the data, because we don't want to basically publish something that turns out to be a fluke that isn't real, but because it was a significant effect, well, we have to pay attention to it now. Here are some other things that you can do. Get a larger sample size. in general. What do we want for Christmas? We want big N. Report all variables that you manipulate. Report all of your findings, whether they square with the story you want to tell or not. Be open about everything. Be honest with everything. Join places like the Open Science Consortium. Pre-register your data, pre-register your hypotheses, and pre-register your analyses. And we'll talk more about this next semester and what these things actually mean. So now let's talk about meta-analysis to examine multiple studies at once. So you're actually going to learn and actually get a chance to try meta-analysis next semester. But here's a quick example that comes from your book. So lying is a pretty creative activity. You have to basically come up with a really good story to basically cover for something that you're trying to hide. So because lying requires creativity and thought that telling the truth may necessarily not, it might stand to reason that people who are about to respond with a lie might take more time in formulating their answer compared to people who are telling the truth. So does lying require more time than telling the truth? And so the researchers who were interested in this did a meta-analysis. What they're basically doing is they are looking at the results of various different studies, and they're basically looking at effect size. So is this a small statistical effect, a medium statistical effect, or a large statistical effect? So a meta-analysis is basically a quantitative analysis that combines the different effect sizes from many different studies that all look at the same thing, and they basically come up with an overall weighted average of the effect. And in general, studies that have more people tend to be more precise, and they tend to carry more weight in a meta-analysis than a smaller sample size does. And so when the researchers did this, they found that the average Cohen's d, the average effect size for lying and time, was a Cohen's d of 1.26, suggesting based on our guidelines for Cohen's d that this is a pretty large, sizable statistical effect. Researchers do find that people who are lying take more time to formulate that lie than people who are telling the truth. What's interesting is that a few different follow-up analyses actually ended up revealing that the effect depends on the instructions as well as the motivation. So if participants were instructed to go as fast as possible, you see that the effect gets even larger. It's a Cohen's d of 1.29 compared to 0.97 when they are not instructed to go fast. When we basically have a motivation to avoid detection, that also modulates the effect. Generally, if they're told to avoid detection, the effect gets smaller. They actually speed up their time in lying. Compared to if there's no motivation. So if they're instructed to avoid detection, that modulates the effect. It kind of lowers their speed. And the same is true if they're trying to avoid detection. So meta-analyses are really useful. They can combine information from multiple studies that are all looking at the same thing and kind of give us a very general idea of what this means in terms of the effect. The problem is that meta-analyses typically will only be looking at studies that were already published. And remember that because of things like questionable research practices, because of p-hacking, because of publication bias, that means that odds are pretty good that the effects of the meta-analysis is basically overestimating the effect that we see. Publication bias favors significant effects. So null results, like we talked about a couple weeks ago, don't get published. Replications don't get published. And the studies that are published may actually be true, or they might be inflated by a variety of different questionable research practices. So for example, this is something I kind of talk about in biopsychology. The effect of certain types of antidepressants like SSRIs, while incredibly useful for some people, it doesn't necessarily work for everybody. Now, if you were only doing a meta-analysis of published studies, what we tend to find, and remember I mentioned that psychology is not the only field that has a replication crisis. I mentioned that, well, biomedical does as well. When we only look at published studies looking at the effects of SSRIs and their efficacy, they're about 94% effective. But remember that published studies, we have a publication bias. When you include findings that produced null effects or smaller effects, when you consider all registered studies, the efficacy of antidepressants is only about 50%, which means that for about 50% of people, it works pretty well, but for the other half of people, not so much. And that's not saying that antidepressants aren't useful, but maybe for some people, they may not be as useful. So I'm going to go ahead and stop here. We'll talk some more about replication next time.